Hi everyone, welcome to another lecture of the subject control system. This is the sixth lecture. In previous lecture, I discussed about translational motion mechanical system, a MassSpringDamper system basically, and then we derived equation of motion of this kind of system, a mass, spring and a damper system. F was the input force and x was the output displacement, and the equation of motion was like this: F equals to m x double dot kx plus bx dot, and then using Laplace transform concept we derive the transfer function of this kind of system. Now let us take another example of this MassSpringDamper system, MassSpringDamper system with another example. Let us consider there is a system like this. It is fixed wall. Okay, here it is a spring and a damper connected with one mass m1, and then there is another damper and spring connected with a mass m2, and an output input force is applied, some displacement x2 and some displacement x1 is happening on the mass, and the spring constant, frictional coefficient, spring constant, frictional coefficient. Okay, so this is the system. Now look here, there is two displacement happening at a time. Let me tell you one thing, we are deriving transfer function of various kind of systems, but transfer function is mainly useful, mainly can be done for single input and single output system, that is called SISO, SISO. SISO kind of system can have transfer function, only SISO kind of system. If the number of inputs is increased or the number of output is increased or both increased, then transfer function cannot be there. I said earlier that state space method is a bit advanced method, so these kind of systems can be represented in terms of state space method, but we can generate individual equation of motions, that is the differential equation, and from that differential equation, one differential equation will be like that, such that it will only relate these two output variables. There will be such differential equation, and because these two output variables are related variables, x1 is dependent on x2. Okay, so these kind of systems for interactive cases, if there is some equation deriving the relationship between x1 and x2, so in the main input output relationship equation we can replace x1, either x1 by x2 or replace x2 by x1, and then that equation will be having only one variable as output, either x1 or x2, because other variable will be replaced by this variable. So now what I want to say is, let's say f is the input to the system, and there is some function f of x1 and x2. From, let's say, by analyzing m2 I am getting this kind of equation. Now okay, initially it is looking as x1 and x2 is input to function f and f is output, but this is not the case. I am considering this is a differential equation, f is a differential, small f is a differential equation of the variable of these two variables. These two variables are the output variables. Okay, now for obtaining transfer function I only have to have only one voltage, either x1 or x2. I cannot have not voltages, it is variables. I cannot have these two variables at a time. Now this kind of system, this is interacting system. For this kind of system, there will be some relationship between x1 and x2. Let's say some function g of x2. x1 is related to x2 by some function g. Then what I can do is I can replace this x1 by g of x2, and the function will look like f of gx2 and x2. Look, the output variable is now reduced only in one term, x2. There is no here there is no presence of x1 here, only x2. So if I consider x2 to be output and f to be input, then I can obtain the transfer function from this equation. Now if I consider x1 to be output and f to be input, then I will replace this x1 by instead of replacing x1 by gx2, I will replace x2 by g inverse of x1. Let me call it another function. Let me call it a function like f1. Okay, and then this equation will look like f of f equals to capital F force equals to f of x1 will be x1, and what about x2? x2 will be replaced by f1 of x1, and then the output will be only x1 and input will be f, as it is a single input system. So this system can be represented in terms of some single input single output system by relating the two different output variables. But this is kind of only mathematical manipulations. There is nothing to analyze from control engineering perspective. This is used for obtaining the transfer function only. What the main analysis portion is to arrive to the differential equation, that is the equation of motions of these two separate objects, these two separate masses. So I am going to first derive the equation of motion for the mass m2. Why I am considering m2? Because m2 is having input attached to it, so I am considering m2 first. I can also consider m1 first, but that is not the concern. The order is not the important thing. You need to the both two equations will be separately independent equations. Whether I am taking m2 as first element, m1 as second element, or m1 as first element, m2 as second element, it will be absolutely no impact on the equation of motions. Okay, so I am considering, for my convenience, I am considering m2 because I like to take the input variable, the object comprises with attached with input variable first. I like to take that, so I am considering m2 as first variable. So m2, the free body diagram of m2 will look like there will be some input force F acting in rightward direction, and one acceleration or displacement, and acceleration will be x2 double dot. Displacement will be in rightward direction. Now what will happen to this spring K2? The spring K2 will be first elongated. That means, okay, let me tell you one thing. When you are analyzing one single object, first consider the other object to be stationary in order to make the direction. Okay, in order to determine the direction of forces, first consider other element to be stationary and then analyze the direction, and then when you are obtaining the expression of the force, then consider the two displacements. I am showing it how I am going to do this. Consider m1 to be stationary and m2 is moving in x2, moving by amount x2, that means in rightwards direction. So the spring will try to elongate itself. Actually this will elongate the spring, and the spring will try to minimize that elongation. So spring will exert a force in leftward direction, that is the restoration force. It will be like this Fk2, and again Fb2 will also be in leftward direction, FB2. Now what will be the expression for Fk2 and Fb2? Now I need to consider the both displacement. Fk2, for Fk2, what is Fk2? The restoration force of the spring in this direction. That means it is actually minimizing the elongation. This force is actually minimizes the elongation. So if this is the spring and this tip is moving in this direction x2 and this tip is moving in this direction by x1 amount, then the net elongation that is happening in this direction is x2 minus x1, isn't it? The next elongation is happening in rightward direction is x2 minus x1. So the restoration force will be proportional to this elongation in rightward direction because it is acting to upwards direction, opposite direction. So the thing will look like K2 x2 minus x1. Okay. And again, if instead of spring I draw the damper, this tip is having displacement of x2 in rightward direction, so having velocity x2 dot in rightward direction, and this having velocity x1 dot in rightward direction, this tip. Now frictional force will be proportional to the net velocity. So what will be the net velocity in this direction? X2 dot minus x1 dot. Obviously then Fb2 will be b2 into x2 dot minus x1 dot. Now we have all the forces. Now we need to determine the equation of motion. So what will be the equation of motion? The equation of motion will be the F resultant is equals to mass m2 x2 double dot. So x2 is happening in this direction, so the acceleration is happening in this direction, so the resultant force in this direction will be F minus Fk2 minus Fb2. If I take, okay, let me first do this, Fk2 minus Fb2 equals to m2 x2 double dot. So what will be the value of F? It will be m2 x2 double dot Fk2 plus Fb2. Why I am taking Fk2 and Fb2 in rightward in right side of this equation? Because Fk2 Fb2 is function of these displacements or the velocities, that means x variables, whereas if this capital F is input variable, so I am considering input to be in left side and output variables and the differential of output variables in rightward side. So what will be the equation then? The equation will just replace these values here, m2 x2 double dot plus, in place of Fk2 I can write K2 x2 minus x1, and in place of Fb2 I can write b2 x2 dot minus x1 dot. This is the equation of motion for this this object. Okay. Now let me analyze mass m1 now. Now again, when m1 is displacing in this direction, then obviously restoring force of this spring will act in this direction, and that will be denoted by Fk1, and the frictional force will be Fb1. Now for this end of this spring, what will it do? Now again, for the direction I will consider, okay, there was a small power cut. We were discussing about obtaining equation of motion of this mass m1. So the mass m1 is displacing in rightward direction, so the spring will try to oppose that rightward direction displacement by some restoring force in leftward direction, and that is Fk1, and the frictional force will be in Fb1 in this direction. Okay, and for K2, now again I am analyzing mass m1, so I am considering for the direction, I am considering first the displacement of mass m2, that means x2 is equals to 0, displacement is 0 for m2, m2 is stationary. For that, what will happen when mass m1 is displacing in rightward direction, then the value the k2, that means the spring k2 will try to compress, will be compressed, and it will try to minimize the compression. So for minimizing the compression, let me draw the spring here. The spring is like this. Okay, now if there is some, if this is stationary and here is some displacement x1 is happening, then the spring is compressed by a displacement of x1, and then the spring will try to oppose by some force Fk, try to oppose this this displacement, this compression. Okay, so now if instead of being stationary, this tip is moving in x2 displacement, moving in rightward direction by x2, then what will happen, we need to consider here the net deformation, that means the net displacement in this direction, that means the net compression, that will be Fk will be k into the net compression will be obviously x2 minus x1, no sorry, x1 minus x2, yeah, x1 minus x2. Earlier the compression, when it was stationary, earlier the compression was x1 itself. Now instead of being stationary, this is moving x2 in this direction, so the net displacement will be x1 minus x2. Okay, now for this spring, again what will be the direction, then spring, this is compression, so the direction will be in this side, Fk2, and again the friction, this is in this direction, so the friction will be in this direction, Fb2. Now as obvious from this portion, you can understand that what is the value of Fk2. Let me list down the values. Fk1, this force is attached with only one displacement, and it will be directly proportional to this displacement k1 x1. Similarly, Fb1 will be b1 x1 dot. And what about Fk2? Fk2 will be K2 into net displacement in this direction, that means net compression is this direction. So x1 is the compression in this direction, and if it is stationary, then it would be x1 only, the compression will be x1 only, but it is moving in x2, moving by x2 amount, so it will be like this, x1 minus x2. And obviously as it is clearly understood that Fb2 will be x1 dot minus x2 dot. Just analyze the system using spring, then you can easily obtain the expression for frictional coefficient. Okay, damper. Now notice one thing, for same spring K2, Fk2 here is acting in this direction, Fk2 here is acting in this direction, that means in same direction the both Fk2 is happening for same spring, but the value, look at the value here, Fk2 is K2 into x1 minus x2, and here the value Fk2 is K2 into x2 minus x1. Why I am talking about this? Because by analysis I am getting x1 minus x2, and here I am getting by analysis x2 minus x1. So what is the problem here? Look, the problem is it is a problem in understanding. Okay, Actually these expressions are right expressions, these expressions are perfectly okay, but the problem is in understanding portion. Sometimes student may ask that same force, same amount of force and same amount of force is acting in same direction, so why the expression is different? That means it is x1 minus x2 and it is x2 minus x1. Why it is different for same spring? Because notice, this force acting in this direction x2 minus x1 is attached with this displacement directly and this displacement indirectly, and it is the force in this end of the spring, and fk2 in m1 direction, this is the end attached to m1, and this x1 is directly attached to the spring, directly attached to the force, and this x2 is indirectly attached to the force, attached to the spring, okay, to the force or to the tip. So this force is acting in this tip, this force is acting in this tip, that's why the two expression is different, that means opposite. There is nothing to be confused about. Okay, now what is the equation of motion for this particle, this m1 object? Look, now x1 is happening in rightward direction, so there will be acceleration in rightward direction, and the acceleration times mass is the resultant force. It is in rightward direction, so the force must be in rightward direction. So what is the force value in rightward direction? Look, all the four forces which are acting in this mass is in leftward direction, so there is no force in rightward direction. So what is the net force in rightward direction is minus of fk1 minus of fb1 minus of fk2 minus of fb2. Okay, understood. Now the equation will be m1 x1 double dot plus fk1, fk1 is k1 x1, plus fb1, fb1 is b1 x1 dot, is equals to minus fk2, fk2 is k2 x1 minus x2, as this is minus fk2, I am writing is in opposite order x2 minus x1, okay, because minus of fk2 is k2 into x2 minus x1, and again b2 into x2 dot minus x1 dot. This will be the equation of motion of this object. Now notice, here x2 is output, x2 is output, x1 is output, x2 is differentiation of output, x2 is double differentiation of output, x1 dot is differentiation of output, sorry I said it as x2, it is x2 dot, x2 dot is differentiation of output, x1 dot is also a differentiation of another output, but output. Now f is input. Now look here, notice here, in this portion, in this equation, x1 is double differentiation of one output, x1 is output, x1 dot is differentiation of output, x2 is another output, x1 is output, x2 dot is differentiation of one output, and x1 dot is differentiation of other output. There is no term related to input force. So from this equation I can get the relationship between x1 and x2. From this equation I can get relationship between x1 and x2, and if I consider x1 to be output, then I can replace x2 variables here in terms of x1 from this equation. First I will write x2 variable in terms of x1 from this equation, and then I will put that x2, the value of x2 here, and I will get this equation in terms of f and x1 only, and then by using Laplace transform I can denote I can use the transfer function as f as input variable and x1 as output variable. And instead of x1, if I consider x2 to be output, I can I can replace x1 I can replace x1 variables in terms of x2, and how I can replace that? I will first represent x1 in terms of x2, x1 variables in terms of x2 variables, and then that that value of x1 variables will be put here in place of x1 variable, that will be replaced x1 by some variable, some function of x2, and this equation will then be only one output, will consist only one output variable, that is x2, and then we can denote the transfer function from with the help of Laplace transform by f and x2 only. Okay, but if, let's say, if I have a system, I need to analyze both the functions at a time, both the variables at the time, both the output. So then I cannot obtain the transfer function, rather I need to go for the differential equation only, or I need to go for other techniques like state space method. Okay, so this is one example of mass spring damper system. Let me discuss another example. I will not go deep into that example because the examples actually the thing is pretty much simple. You just need to take one object and draw the free body diagram. After drawing the free body diagram, just consider the compression and elongation of the spring. Then from the spring you can get the expression of the force, restoring force of the spring, and then similarly that frictional force will be having the same kind of expression, but the distance, that means the displacement will be velocities, will be replaced by velocities, and then just calculate the resultant force in the direction same as the displacement x2 of that object, and then obtain the differential equation or the equation of motion. So why I am taking another example is I need to tell you something. Okay. I said that the spring is the damper is actually denoting the friction. Now if I have been given a system like this, let us say there is a mass, connected with the wall by a spring, and there is another mass and another spring, another spring and another damper connecting another mass m2. One force is applying, and this is having x2 displacement, this is having x1 displacement, same. And now I need to analyze this system, but the system is not only this portion. The ground line is extended like this. This is okay. This thing represents a steel wall or steel floor. Okay. I am using Bengali terms sometimes. Okay, so this is kind of a steel wall. Steel means not steel. It is steel means stationary. Okay, stationary wall, stationary floor, stationary ceiling. It can be that. So there, instead of having a damper connected to it, there is mentioned that here is a frictional coefficient of B1, here is a frictional coefficient of B2. That means the lower part of the lower surface of the mass and the floor is having some frictional coefficient of B1, and similarly for mass M2 is having some frictional coefficient as B2. So instead of connecting a damper between them, they can represent the system like that. So we will first replace this system in terms of some mass spring damper. Okay, first we will, okay, it is B, let's say. So how we we draw the standard diagram from this? Look, this spring is connected to this wall, no issue. This mass is connected, mass m1. Now this mass is having some frictional coefficient, friction with this surface. So this surface is the ground surface and this surface is the ground surface, again the stationary surface. All the things will be with respect to this stationary surface. So if there is frictional coefficient between this surface and the stationary surface, so that will be same as connecting a damper between this mass and this stationary what we call stationary surface. Okay, because this is also a stationary surface and this mass is moving. Now this mass is moving and this is a stationary surface. So here it is having K1 and it will be having B1. This again there will be having some factor K2 and some damper as it is given in the system diagram. M2, it will be having mass M2 and the mass is having some input F, some output X2. Here I have some output X1. Now again, how I am going to model this portion by a damper, this friction. Again, this mass is moving, M2 is moving, and this is a stationary, this is a stationary. So the frictional coefficient, the damper will act between the stationary portion and the moving M2 portion. And this is B2 here. Now it is pretty much simple. Now we can draw easily the free body diagram of mass M1 and M2, and then from that free body diagram we can calculate the expression of individual elements, and by that we can arrive to the differential equation. I am not going to do all the things again. I just need to tell you that this kind of system can be represented in this kind of system. That means sometimes in question you may not have seen always like this kind of representation. Some damper can be missing there, some damper can be missing there like this also. Let's say you have one mass, okay, force. Okay, so how you can model this thing in this diagram? Let's say here it is having a frictional coefficient of B and K, this spring. Now again, if there is frictional coefficient given, then consider there is a damper like this. If it is not given, then consider there is no friction between this surface and this surface. And often it may be used that there kind of some kind of wheels can be connected in there to denote that there is no friction. Okay, because using of wheels can be used to minimize the friction. So by wheels they mean to say that there is no friction between these two surfaces. So how you are going to model this system? Let's say this is the stationary portion, a spring is attached to this mass M1 and there is no friction between this mass and this stationary surface, but there is another mass M2 which has some friction with mass M1. That means this. Now this is the force. Again, I said earlier that I drawn earlier that the force was here. This can be, if this is the case, then there will be the force. Okay. So any this kind of system, I am not going to discuss how the complex system can be represented in terms of mass spring damper, but sometimes questions may be formed in this diagram, in this kind of diagram. Then you need to first transform into simpler one, the standard diagrams. Okay. Now translation motion is completed here. Now I am going to discuss the next topic related to translation and motion only, that is force voltage analogy. Force voltage analogy. Okay. What is force voltage analogy? Now, as I said, any electronic or any system can be represented in terms of some electrical, some R, L and C elements, interconnection between them, some circuit like that, and some independent and dependent voltage and current sources. Anything that can be an op amp, that can be a transistor, anything can be represented in terms of simple R, L and C. And again I said that any physical system can be represented in terms of some mass spring and damper system. Now what happens is, though this is pretty simple to analyze the mass spring damper system and to obtain the transfer function, but to manipulate this kind of system in this mass spring damper diagram is sometimes it may not be some handy. So in those scenarios we actually use to convert those mass spring damper system into an electrical equivalent. How we can do that? There are two different kind of technique. One is force voltage analogy, another one is force current analogy, where force is considered to be a voltage. Sorry, the voltage spelling is wrong here. Okay, so force is this is called actually analogous system, an electrical analogy of the physical system. That means representation of the physical system by means of some electrical system. Okay, so force voltage analogy and force current analogy. In force voltage analogy, what we will do is we will consider the force to be to act as the voltage, and in force current analogy we will consider the force to act as current, and the mass, the damper, the spring, the output displacement or velocity will be some different element that will be analyzed and discussed whenever each of the thing, force voltage or force current, is discussed. Okay, let me first start discussing force voltage analogy. So here, as obvious, force is considered to be voltage. Force is considered to be voltage. Now I said earlier, if it is a series RLC circuit, why I am considering series RLC circuit? Because if it is parallel RLC circuit, then voltage will appear across all the elements and that will not work actually. So VIT RLC, VIT is the input voltage. Okay, now if I consider the current, the voltage current relationship of this circuit will be VIT minus I into R, IT into R, minus L DIT dt minus 1 by C integration I dt equals to 0. Simple KVL. Okay, I am writing KVL from here to here. Now I can write it as VIT equals to IT into R L DIT dt 1 by C I dt. Now look, there is an integral term, but whenever we are dealing with the force systems like translational system, there was no integral terms. The thing was like F equals to m x double dot b x dot and k x. There was no integral term involved, but here it is integral term. We need to get rid of this integral term. We know I equals to dq dt, that means the rate of change of charge. So obviously I dt, integration I dt will be q, the amount of charge. So let us replace the current elements with the equation as like charge. Okay, so it will be dqt dt r into dq dt plus L dit dt, that means d2q dt2, and 1 by C will be q vit. Now in dot form, let me write it in dot form, that will be easy to visualize. R, okay, L q dot, L q double dot, R q dot, 1 by C q. Now look this equation, let's see number 2, and this equation is number 1. Consider this, compare this number 1 and equation number 2. What is happening? The force voltage analogy, force is equivalent to voltage, so the force is equivalent to the voltage. Then what will happen is x double dot is equivalent to q double dot, x dot is equivalent to q dot, x is equivalent to q. So charge will be replaced by, that means displacement will be replaced by charge, force will be replaced by voltage, velocity x dot will be replaced by q dot, and q dot means current I, and again mass element will be replaced by inductive element, m is replaced by L, frictional coefficient will be replaced by resistance, spring constant will be replaced by 1 by capacitance. So from this actually comparison, we can convert any mass spring damper system into some equivalent RLC circuit, and that will be lot more easier to handle and lot more easier to actually analyze. That is why this kind of thing is introduced in this is called analogous system. So let me summarize. For force voltage analogy, force F will be voltage, displacement x will be charge q, velocity x dot will be current q dot, that means current I, mass m will be inductor L, frictional coefficient will be resistance R, spring constant will be reciprocal of capacitance. So if you can remember these comparisons, these conversion, then you can convert any mass spring damper system into some RLC voltage current relationship between them. Okay. So this is the summary for force voltage analogy. Force will be replaced by voltage, displacement will be replaced by charge, velocity will be replaced by current, mass will be replaced by inductor, frictional coefficient will be replaced by resistance, and spring constant will be replaced by 1 by C. So now look one thing, mass element is equivalent to an inductor. Now in a circuit, if voltage is the input, that means force to voltage, force is input to voltage input. If voltage is input, then we can consider inductor to be acting as mass, equivalent to mass, resistor to be acting as a damper, and a capacitor to be acting as an inverse of spring. That means the thing spring do, the things that a spring does will be exactly opposite to the capacitor, because spring constant K will be replaced by 1 by C, that means the reciprocal of capacitance. Okay. Now there is another analogy, that is force current analogy. Let me do that. You have written this thing. Let's not erase this one, because this is for force. Until and unless there is force, that means if there is force involved in any analogy, this will be helpful. Now in place of voltage I am writing is a current analogy, force current. Now I am using current as input variable here, because force was input. So if I convert force to current, then current must be the input variable. So if current is the input variable, then obviously the circuit must be one parallel combination of RLC, because if the current is, if there is a current source like this, and if it is a series combination of RL and C, then current through each element will be I itself. There will be nothing to actually analyze. So current is obviously used for parallel circuits. Here it is a resistive element, IT. If I consider Vt to be the voltage across each element, then obviously IT will be IR plus IL plus IC. How will be IR? IR is voltage by the resistance Vt by R. IL will be Vt, that means L, sorry, V means V is L di dt, we know that. So 1 by L V dt will be I. And IC is C dVt dt. Now again, This equation does not have any integral term, but here I have integration of voltage. Now voltage can be represented as the rate of change of flux, magnetic flux. Voltage can be represented by rate of change of magnetic flux. So the amount of flux is equals to integration Vt. So this integral term can be represented by psi, and each of the term can be represented by some differentiation form of psi t. So 1 by r Vt is d psi t dt, it is psi t itself, it is d2 psi t dt2. This is the equation here. Now again I am writing it in dot form, C psi double dot t, let us not consider t, psi double dot plus 1 by r psi dot plus 1 by L psi. Now again I can compare these two equations, equation number 1 and equation number 2, and I can arrive to the conclusion that force is equivalent to current, displacement x is equivalent to magnetic flux, velocity x dot is equivalent to psi dot, that means the voltage, acceleration x double dot is dvdt or d2 psi t dt2, this one, and the mass element is the capacitance, the B is equivalent to 1 by r and the spring constant K is equivalent to 1 by L. So F is equivalent to I, okay, X is equivalent to psi, X dot is equivalent to V, M is equivalent to C, B is equivalent to 1 by R and K is equivalent to 1 by L. Now as earlier I am writing down the summary clearly. Now force F is equivalent to current I, because it is a current force current analogy. Displacement x is equivalent to magnetic flux psi, velocity x dot is voltage Vt, mass M is capacitance C, frictional coefficient 1 by r, reciprocal of resistance 1 by r, spring constant reciprocal of inductor by L. These are the force current analogy. That means force can be replaced by current, displacement can be replaced by magnetic flux, velocity can be replaced by voltage, mass can be replaced by capacitance, frictional coefficient can be replaced by reciprocal of resistance, and spring constant can be replaced by reciprocal of inductance. Inductor, it is not inductor, it is inductance. Okay. Inductor is the name of the element, and inductance is the value, or inductance is the behavior of the element, is the property of the element. Okay. So this is force current analogy. From next day I will start the rotational mechanical system. There we will learn again, spring will be there, damper or dashpot will be there, and in place of displacement there will be angular displacement, that is theta. In place of force there will be torque, tau, and then we will go for torque voltage analogy and torque current analogy. Hope this is clear for clear to you. I think the time is pretty over now. I am closing today's lecture. Thank you. See you in the next lecture.